Welcome to an exploration of one of chemistry's most fascinating contradictions, the Maillard paradox. The same chemical reaction that creates the delicious flavors we love in grilled steak, toasted bread, and roasted coffee also produces compounds that could potentially harm us. First, let's understand what the Maillard reaction actually is. The Maillard reaction is a chemical reaction between amino acids from proteins and reducing sugars that occurs when we heat food. It was first described by French chemist Louis-Camille Maillard in 1912, though its importance wasn't fully recognized until decades later. The basic equation shows amino acids plus reducing sugars heated together, producing brown pigments and complex flavor compounds. Here's a simplified view. Proteins and sugars, when heated together, transform into the brown, flavorful compounds we associate with cooked food. Temperature is absolutely critical for the Maillard reaction to occur. The Maillard reaction requires temperatures above 140 degrees Celsius, or 284 degrees Fahrenheit, to proceed at significant rates. The activation energy is approximately 100 to 150 kilojoules per mole, which explains why heating is essential. This graph shows how the reaction rate dramatically increases once we cross that 140-degree threshold. Below this temperature, the reaction proceeds extremely slowly. Here's an interesting question. Why doesn't boiling water create Maillard flavors? The answer is simple. Water boils at 100 degrees Celsius, which is below the Maillard reaction threshold. This is why steamed or boiled foods don't brown. The Maillard reaction isn't a single step, but rather a complex three-stage cascade of reactions. Stage 1, initial condensation, where amino acids and sugars combine. An amino group from a protein reacts with a carbonyl group from a sugar, forming a Schiff base and releasing water. An amino group and a carbonyl group come together, forming a Schiff base intermediate compound. Stage 2, the Amadori rearrangement, named after chemist Mario Amadori. The Schiff base undergoes a molecular rearrangement to form a more stable Amadori product. Stage 3. The Amadori product breaks down into hundreds of different flavor and color compounds. This produces melanoidins, the brown pigments, plus hundreds of volatile flavor compounds that give foods their characteristic tastes and aromas. Let's explore the desirable products of the Maillard reaction. The Maillard reaction can produce over 1,000 different flavor compounds, creating incredible complexity. Different conditions produce different flavor profiles: nutty, meaty, caramel-like, and many others. Let's look at some specific flavor molecules created by the Maillard reaction. Pyrazines create nutty and roasted flavors found in coffee and roasted nuts. Furans produce caramel and sweet notes, giving baked goods their appealing aroma. Diaphenes, containing sulfur, create meaty and savory flavors in grilled and roasted meats. Now let's examine the concerning side of the Maillard reaction, acrylamide formation. Acrylamide is classified by the International Agency for Research on Cancer as a probable human carcinogen. Acrylamide forms specifically when the amino acid asparagine reacts with reducing sugars at temperatures above 120 degrees Celsius. Asparagine, a common amino acid found especially in potatoes and grains, combines with sugars under heat to form acrylamide. You might wonder, why is asparagine particularly problematic? Asparagine has a unique side chain structure that makes it especially prone to losing an ammonia group, which is the key step in acrylamide formation. Let's look at actual acrylamide concentrations in common foods to understand the scale of exposure. Acrylamide is measured in micrograms per kilogram of food. Typical acrylamide levels. Bread contains about 50 micrograms per kilogram, coffee around 150, French fries 350, and potato chips can reach 450 micrograms per kilogram. For an average adult, daily acrylamide exposure is estimated between 0.5 and 2 micrograms per kilogram of body weight. For a 70-kilogram adult, this means approximately 70 micrograms of acrylamide exposure per day. Assessing the actual health risk from dietary acrylamide is scientifically challenging. Animal studies clearly show carcinogenic effects, but at doses much higher than typical human exposure. Animal studies typically use doses 1,000 to 10,000 times higher than average human exposure levels. Human epidemiological studies have shown mixed results, with no clear consensus on cancer risk at dietary exposure levels. We see a clear dose-response relationship in animal studies, but human epidemiological data is much more scattered and inconclusive. Temperature and cooking time are the two critical variables that determine acrylamide formation. Acrylamide formation doesn't increase linearly with temperature, it increases exponentially. The acrylamide concentration is proportional to E to the power of temperature over a reference temperature. This exponential curve shows how dramatically acrylamide levels increase as cooking temperature rises above 120 degrees Celsius. Cooking at 190 degrees Celsius versus 170 can double acrylamide levels in many foods. Additionally, longer cooking times allow more acrylamide to accumulate, though the rate of increase slows over time. Now we can truly understand the paradox. How does one reaction create both delicious and dangerous compounds? The key insight is that the Maillard reaction is not one reaction, but hundreds of parallel chemical pathways occurring simultaneously. From the same starting materials, multiple reaction pathways branch out. Most produce desirable flavor compounds, but some pathways lead to potentially harmful products like acrylamide. Different amino acids preferentially take different chemical pathways, which is why asparagine specifically leads to acrylamide. Asparagine follows pathway A to acrylamide, while other amino acids follow paths B through Z to produce the various flavor compounds we desire. Several factors influence the balance between good flavors and harmful compounds. Factor 1. The amino acid composition. Foods high in asparagine, like potatoes, are more prone to acrylamide formation. Factor 2. Sugar content. Foods with more reducing sugars produce more Maillard products overall, both good and bad. Factor 3. pH level. Acidic conditions actually reduce acrylamide formation while still allowing flavor development. This diagram shows relative acrylamide formation. Foods high in asparagine produce much more, medium levels produce moderate amounts, and low asparagine foods produce minimal acrylamide. Given this knowledge, what practical strategies can we use to reduce acrylamide while preserving flavor? Strategy 1. Lower your cooking temperature by 10 to 20 degrees Celsius. This can reduce acrylamide by 30 to 50% while still achieving good flavor. For example, reducing frying temperature from 190 to 170 degrees can cut acrylamide formation roughly in half. Strategy 2. Avoid overcooking. Aim for golden yellow rather than dark brown color. These color guides show what to aim for. Light golden and medium golden brown are good. Dark brown requires caution, and very dark or burned should be avoided. Strategy 3. For potatoes, soaking cut pieces in water for 15 to 30 minutes removes some sugars and reduces acrylamide by up to 40%. Strategy 4. Never store raw potatoes in the refrigerator. Cold temperatures convert starches to sugars, dramatically increasing acrylamide potential. Store above 8 degrees Celsius. Strategy 5. Adding acidic ingredients like lemon juice or vinegar can inhibit acrylamide formation while enhancing other flavors. Let's step back and look at the bigger picture of risk versus benefit. The Maillard reaction is essential for making food palatable and enjoyable. Without it, most cooked foods would be bland and unappetizing. Complete avoidance of Maillard products is neither practical nor necessary for most people. Here's a comparison. With controlled cooking techniques, we maximize benefits while minimizing risks. Uncontrolled high-temperature cooking increases risk without proportional benefit increase. The key is moderate consumption combined with smart cooking techniques we've discussed. Acrylamide isn't the only concerning compound formed during cooking. Heterocyclic amines form specifically in muscle meats cooked at high temperatures, particularly when charring occurs. Amino acids react with creatine at temperatures above 200 degrees Celsius to form these heterocyclic amines, or HCAs. Polycyclic aromatic hydrocarbons, or PAHs, form from smoke and direct flame contact with fats. Advanced glycation end products, known as AGEs, also form from sugar-protein reactions and may contribute to inflammation and aging. The Maillard reaction network produces not just acrylamide but also heterocyclic amines and advanced glycation end products under certain conditions. You might wonder, why not just eat everything raw to avoid these compounds?